the relationship between Ka and Kb and Kw. Hopefully you remember that our Ka was our acid dissociation constant. Our Kb here was the base dissociation constant, and our Kw was the ion product constant of water. Now let's have a look at a relationship between all of these. Why is it important to establish this relationship? Let's take an example of CH3 COOH, also known as acetic acid. Okay, we're going to make this dissociate and ionize into its respective cations and anions, but we're also going to get its respective conjugate base and do the same thing, and then we're going to be able to establish an interesting relationship. So I'm just going to label this here as number 1 first. We're going to get our CH3COOH. We're going to dissociate it with water. Now what's going to happen? Well, we're going to have obviously a reversible reaction here. What is it going to produce? Like I said, its respective cations and anions. Well, this here is an acid, right? Isn't this acetic acid? So let's just label down here that this here is the acid. So if this is the acid, vice versa, this needs to be the base as its counterpart. So if this acid gets dissociated with this, what's going to happen? Well, this will eventually become its conjugate base, right? So it's going to become a conjugate base, and you should remember in our previous videos how conjugate bases work. A conjugate base is whatever is left over and whatever is formed after this hydrogen, this proton, gets donated. Okay, see the link in the video description if you need more details about this. So this one is going to be removed, right? So if it's removed, what is it going to be left with? It's going to just be left with this, right? CH3COO. And of course, that is going to result in just a charge because of that removal of that H. Okay, it's a little bit more negative right now. So that we have there. Now we're going to be giving our H2O. Okay, where does this go? It goes over here, so that is going to accept it, because remember the definition of a base is a proton acceptor. So that H2O becomes now an H3O. There we have it. So again, this here would then be the conjugate acid of this base. Now, let's get this conjugate base over here, like I said, and let's have this dissociate with water as well. So let's bring this down over here. So this is going to be number 2 now. So this is going to be CH3COO1 minus, and we're going to have it now dissociate with the water. Now what's going to happen here? Well, this here is going to be labeled as our base right now. And this here is going to have to then become the acid, okay? Remember, this is the conjugate base, but we're doing it on its own now. So now we're focusing in respective as it is a base. And we're just going to get now this dissociated with the water. What do we end up getting? Well, remember, this here is a base, right? So a base is a acceptor of the proton. So it's going to take a hydrogen, okay? As opposed to up here where it lost that hydrogen, it's going to now take it, okay? So then this is going to become CH3COOH. Okay, and then this here would now be labeled as now the conjugate acid of that base that is now in question. So then this got added over here. So then what's left over here for this acid, right? This then becomes just OH, okay, just one H instead of 2. So we have OH now. And this would now become the conjugate base of this acid. Again, remember, a conjugate base is whatever is formed after that H has been removed. Okay, so now that H has been removed, now it's labeled as the conjugate base. Okay, just like over here that H got removed, it's now labeled as the conjugate base. Now, we're just going to get the Ka and the Kb of each one. What do I mean by that? We got to get the expression, the Ka expression of this one over here, and the Kb expression of this one over here. Now, why is this one the Ka versus this one here, which would be the Kb? Because this here is dealing with the acid, okay? This one here is dealing with the base, hence why this would be a Ka and this would be a Kb. All right, let's try the Ka over here. The Ka is going to be these two products. So we have CH3COO and we're going to multiply it by the H3O. Okay, by the way, this has to be a plus up there. I forgot about that. Now it's going to be given on the bottom. Well, it's just going to be this one because this H2O gets reintegrated into the Ka, so we're not going to put that in the denominator. So the video link in the description if you're confused about that. There we have it. So that's it for our Ka. Let's do the same thing for our Kb. We're just going to get our products in the numerator. And of course, this is going to be in our denominator now, CH3COO minus. Now let's look at the relationship between these two. As you can notice, the product of these two constants yields something very interesting. In case you're confused, let's stack them right beside each other. So let's have our Ka over here and our Kb over here. So here we have it drawn out. We're just going to cross multiply. Look what happens. Obviously this and this is going to cancel out. This and this is going to cancel out. What do you end up getting? You end up just getting our hydronium and our hydroxide. Okay, so I'm just going to write here on the side the product of these two, because we just multiply them so that we were able to cancel out our units, so that we were able to cancel out our like terms. What we have now is the product of these two constants, right? This is the one constant, this is the second constant. Create or yield our hydronium and our hydroxide. What does this mean? Well, this would mean that our Kw, remember our ion product constant, is therefore going to equal our hydronium and our hydroxide. So we can actually shorten this down as Kw is equal to our Ka times our Kb. Since the overall equilibrium constant is the product of these individual equilibrium constants. This has its own individual equilibrium constant. This has its own individual equilibrium constant. So let's write that over here. The overall equilibrium constant is the product of individual equilibrium constants, and now I'm going to take it from a different angle over here, because this can actually be shown with a sum of two or more reactions. For example, what do I mean by this? For example, I'm going to treat this that I'm going to be showing you shortly, treat them as the addition of the reaction sequences. Let's have a look over here. We're going to get our CH3COO H plus the H2O, what we got earlier, right? This was our acid. It's dissociating with the water so they can ionize to form our cations and anions. What do we get in the beginning? We got CH3COO 1 minus plus the hydronium, right? What do we get after that? Okay, we started with our conjugate base. So then our conjugate base did the same thing with the water. And what did it create? Its respective anions and cations. So we're just drawing this out again, but we're now going to be adding them as reaction sequences. So just like how you would create a net ionic equation, we're just going to cancel out our like terms. Well, we have this here as a like term of this. We have this here as a like term of this. And the only thing that we have on our reactant side now is our H2O. But there are 2 moles of each, so we'll just put 2 H2O over here. And of course, this is going to be our H3O plus added with our OH minus. As you can see, this makes sense because our H2O here is representative of the ion product constant of our H2O as indicated over here. Have a look at this practice question. List the conjugate bases for each acid. Well, for A, we have HiO4, our periodic acid. From here, in order to make it as a conjugate base, remember the conjugate base is what's left over and has formed as a result of losing that proton. And that proton would be this hydrogen in question. So if we remove that and got rid of it, what do we end up getting? We just get just IO4, okay? And then of course, because that's gone, we're a little bit more negative, so we now have a negative charge over there. So this is the answer. This will be IO4. What about cyanic acid? Well, our cyanic acid is HCNO. Same thing, we're just going to get rid of that hydrogen. We end up just being left with CNO, and then we're a little bit more negative, so we get that negative charge over there. This is the answer. Now, write the Kb expression for each conjugate base above. Well, let's start off with A first. So again, it's telling us to make the expression for each conjugate base. Okay, and we know why they're saying that it's a Kb expression, not a Ka expression. It's because we're going to be treating this conjugate base here as the base. As you can see, there is a base within the name of our conjugate base. So we're just going to be looking at this from the lens of a base. Okay, so it's going to be accepting a hydrogen. So it's going to be accepting a proton. So let's get this base here in quote unquote here, our base. Okay, let's write it out over here on the side. So we're going to get our IO4. And it's going to be added with our H2O. It's going to dissociate, so it can ionize in order to create our cations and anions. Remember, this is a base here, so it's going to be taking that hydrogen from there. So what is it going to be given? It's going to now be given an HiO4. Now, what's left over? Well, this got removed, okay? So we only have one H now, so we just get OH. This here is our hydroxide. Now we can easily create our Kb expression. Well, remember, our Kb expression is an equilibrium constant, just like any other equilibrium constant, like a KEQ generally. So our Kb will have our products on the top, and then our reactants on the bottom. So let's have our HiO4 multiplied by our OH minus, and then on the bottom let's have our IO4 1 minus. There we have it. That here is our expression. We can do something similar for our B over here. Again, it's also going to be a Kb expression. We're just going to deal with our CNO minus over here. Going to add it with our H2O. What is it going to create? It's going to take, this is going to take that hydrogen from over here, so it's going to end up becoming HCNO, and then this is gone, so we just get a 1H, so we just have a hydroxide. That's it. So now let's create our Kb expression. We got our products on the top, HCNO multiplied by our OH minus all over our CNO minus. There we have it. That's it. Okay, let's look at this question over here. In order to do this question, you will be needing to get something like this. You can get this from Appendix B or whatever textbook that you're looking at near the back, because they tell you the specific ionization constants for Ka and Kb. Okay, these are just some of them. It's not all, okay? However, you will also likely be given this from your teacher as a little sheet, okay, just prior to your quiz or test assessment. So let's have a look here. A Kb value for the conjugate base. Well, we're just going to be dealing with first our hydrosulfuric acid, right? So let's write this out. We know hydrosulfuric acid is just going to look like this, right? And we have to get the Kb value for the conjugate base of this hydrosulfuric acid. So what would be the conjugate base of this hydrosulfuric acid? Well, we have to get rid of this H, right? Because whatever is formed after that hydrogen proton is removed is going to be our conjugate base, so it's going to be HS. And now it's a little bit more negative. Okay, so this here is our conjugate base. What is the Kb value of this? Well, let's look for hydrosulfuric acid. Well, we see this right over here, okay? And we see that its Ka value is simply 8.9 times 10 to the negative 8. So let's write that on the side here. Now what do? Well, we're going to get this Ka value and plug it into a specific formula. You should know that our formula for Kw is equal to Ka times Kb, okay, which we just announced together. So our Kw, we should know that its constant value is 1 times 10 to the negative 14. We know that our Ka value is simply 8.9 times 10 to the negative 8. And then we're just going to multiply by our Kb. We're trying to find what that is. So this is a simple isolation. Now we just divide it by 8.9 times 10 to the negative 8 divided by 8.9 times 10 to the negative 8. Oops, times 10 to the negative 8. Okay, cancel these out. What do we end up getting for a Kb value? We're getting 1.12. We'll just do it in 2 decimal places, times 10 to the negative 7. That's the answer. Let's have a look at this question over here. Find the Ka value for the conjugate acid of dimethylamine. Okay, you should already know how to create this, okay, without having to look down here. But that's only if you've learned organic chemistry. We haven't covered organic chemistry in our series yet, so I'm just going to say look down here for now for you. So we have CH3. There's going to be 2 of them, and H. What is going to happen after that? It's going to create its conjugate acid. Remember, a conjugate acid is what is formed after it's received an extra hydrogen, an extra proton, okay? So it's going to obviously be now NH2. Okay, and it's a little bit more positive now because of that addition of a proton, so now it has a plus sign up there. Okay, and as you can see, that checks out over here. We know that its Kb value is 5.4 times 10 to the negative 4. So what we'd be doing over here? Well, we're going to obviously get our formula and then just enter in our values that we know about. Ka, we're trying to find, that's going to stay. Kb, we now know it as 5.4 times 10 to the negative 4. Oh, times 10 to the negative 4. Okay, so we're just going to now divide, get rid of it, do it on the left side. What do you end up getting for our value answer for our Ka? You end up getting 1.85 times 10 to the negative 11. That's the answer. Now these two are the 2 green questions of the day. This is the first one, this is the second one. For this example, I want you to obviously pause the video, try these 2 yourself. This one should be not a problem, but for this one over here, I'm definitely going to want to show you how this works out because it could be a little bit tricky, and I do think that it's needed, it's warranted for me to give a rundown explanation of this, okay? But I do definitely want you to try this on your own first, okay? So please pause the video, and I'll be giving you the answers shortly. The Kb expression for a conjugate base is simply the reciprocal expression of the K expression for the acid of that conjugate base. Okay, let's stop that right over here, okay? Because after that, it's now asking us to verify our answers of writing the Ka and Kb expression using ammonia as the example. But first, we got to get our template, okay? So let's just focus on the top here and chunk it down. So we have our Kb expression for our conjugate base. Well, if we're going to get our conjugate base Kb expression, we have to know where it came from. So we're just going to write, like always, our acid plus our base. Whenever you have an acid, there's going to be a counterpart base to it and vice versa, and it's going to create what? It's going to create its particular anions and cations, right? Well, right now we're going to focus on this acid because an acid eventually becomes its conjugate base. Okay, and remember, a conjugate base is whatever is formed after a hydrogen has been removed. So if we get this hydrogen from this acid and we remove it away, what's going to happen? It's going to become a little bit more negative. So this thing over here is going to be our anion. Okay, so our anion here is technically going to be our conjugate base. It's going to be a little bit more negative now, as opposed to a base where it receives that proton, and now it's going to become a conjugate acid. So that conjugate acid is going to be a little bit more positive because it received that proton. So this one over here, our cation, is then going to be our conjugate acid. So what we're going to be doing now, again, the question is asking for the conjugate base. So that's what we're going to be getting over here. Our conjugate base over here is now going to be acting as a base. Okay, you can put down here, if you're a little bit confused, okay, conjugate base if you want. It's up to you, but it's now going to act as if it is a real base right now, hence the base in its name. So this base right now is then going to add with another acid, likely water, so that it can dissociate and create its own cations and anions. Well, what's going to happen? Well, this base over here, what is it going to make? It's going to now make its constituent conjugate acid. It's conjugate acid over here, okay? And then this base over here, it's going to turn it into its conjugate base. So if we were to get our Kb expression of this whole thing, okay, and remember we're revolving around our conjugate base over here, which is acting like a base, so we're now going to get our Kb value of this expression over here. And just like any other equilibrium constant, our products go on top and then our reactants go on the bottom. So we have our conjugate acid up here multiplied by our conjugate base. And then on the bottom here is going to be our denominator. This one obviously gets integrated within the Kb. Okay, it's likely going to be water. So we're just going to be putting our con base or our base down here. This here is going to be our Kb value. So what I'm going to do is get this expression over here and save it up here, and we can compare and contrast it with the Ka, okay, because we're going to do the same thing over here, our Ka expression for the acid of that conjugate base. So now we've written it up over here. What is it now asking for? It's asking for the Ka expression for the acid of that conjugate base. Well, this over here was the expression for that conjugate base, right? So now it's pretty much asking to do the former, the one before. Because if this here was our conjugate base and we just found it, again, this here is a conjugate base that I just talked about, okay, this one over here. Well, it's saying find the K expression of the acid for that conjugate base, okay? So what is the acid for this conjugate base over here? It's obviously going to be this one. So we've already kind of done it. This acid over here, okay, this expression revolving for this acid, it's kind of already written out. We just pretty much write out this whole expression within our constant expression formula. So we're just going to be putting our Ka over here, and we're just going to put these as our products and these as our reactants below in the denominator. So let's try this numerator, this, and the denominator. So we're going to be putting our here, our conjugate base. So let's write that here, our conjugate base multiplied by our conjugate acid. And we're going to divide this all by our denominator, just our acid. There we have it. So now we're just going to compare between these two. As you can see, how do they stack up against each other? Well, it's pretty obvious that they are not a reciprocal of each other, right? It's asking, are they a reciprocal? Okay, reciprocal expression of one another. Is the statement true or false? Well, there's no way that can be possible because we have an acid down here, okay, and it can't be a reciprocal up here because we have a conjugate acid up there. Our base down here is not a reciprocal up here because the base is down here, it's not up here, okay? We don't see like terms over there. In fact, we have a base down here, we have a conjugate base up there, okay? So obviously this is not going to be a reciprocal, so this is obviously going to be false. However, the question is asking us to use ammonia as an example. So let's give it a try. So I've written it out over here. They did say to use ammonia as our base. Okay, so we're just going to be putting NH4 or NH3 over here as our base. And in terms of our acid, what's going to happen with this ammonia? Well, this ammonia is, again, the base, so it has to receive that extra hydrogen. So the extra hydrogen goes onto this NH3. Okay, so then it becomes our NH4. Remember, when it receives a hydrogen, what is formed left is our conjugate acid. So that would be this one over here. So we have an NH4. Okay, it's a little bit more positive, so we have that positive symbol up there. How about for our conjugate base? Well, again, this is going to be our little H2O. Let's write that over here. Of course, this got the hydrogen from this acid, so what we're left with is just an OH minus. We'll put an OH minus over here. Now, we can do something similar for this one up here, okay? What is going to be our acid? Well, if this used to be the base, that means our acid up here must have been our NH4. So let's put that over here. And then what would our base have to be? It would have to be our H2O. And then from here, we just need to be able to show where this acid became its respective conjugate base. So this NH4 over here, it has an extra proton that it needs to donate. It's going to donate it away, so it's going to become NH3. Where's that H going to go? It's going to go into our base because bases are acceptors. Then it's going to become H3O. There we have it. So if we were to stack these up against each other one more time, and let's put our equilibrium constant. Again, this is going to be our Ka, and this here is going to be our Kb. And let's put our NH3 on the top, and our H3O on the top. And then on the bottom here we have our NH4. For our Kb, we have our NH4 on the top. And then we have our OH on the top. And then our bottom is going to be our NH3. So as you can see here, look at the Kas. We see an H3O plus in the numerator up here. Look at our Kb. There is an OH minus in the numerator. So this is impossible for it to be a direct reciprocal of one another. And this is the answer to the second question.